Hello. 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 Welcome. Welcome, everyone. Anybody who's here? Nobody's here yet. Well, let's go ahead and get started anyway. Okay. Wisdom, can you hear me? All right. Thank you. Just making sure. It's been a while since I've done this. But anyway, so let's go ahead and get started. I'm just going to go ahead and do random projectile motion things until somebody suggests something else. But so let's go ahead and do a classic. You know what? We solved for delta y earlier today. Let's go ahead and pick a thing right then and solve for delta x thrown at, let's say, 6 meters per second. And I want to know delta x, delta t, vy, and resultant velocity. And let's go ahead and, since I have a K-kid looking now, let's go ahead and calculate our angle at the end, okay? So first things first, I said, when in doubt, calculate time first. So let's go ahead and start calculating time, okay? Okay, now I can actually see the chat and everything. So delta, okay, so delta time. Now, we know how far we're falling. We know our delta y, and we know our acceleration. So we can go ahead and calculate our time pretty easily. Let's start with our displacement equation. And again, because our initial velocity in the y direction is 0, we can go ahead and strike that out. Next, we can plug in our numbers. So we have negative 30 meters because we're falling down equals 1/2 times negative 9.8 multiplied by whatever the time is squared. Divide both sides by negative 9.8 multiplied by 1/2. Those cancel out. Let me go ahead real quick. I forgot to bring my good calculator home, so I'm using my phone as a calculator. Divided by 9.8. And then, so delta t squared is 6.12. Square root both sides. And our time is equal to 2.47 seconds. Okay, so let's go ahead and write that in to our little answer table over here. And now, since we know that our Vx is 6 meters per second, we can go ahead. Okay, good question, Wisdom. We'll get to that in just a second. Wisdom just asked, when does acceleration equal 0? We'll talk about that in just a second. We were talking in the y direction, so our acceleration due to gravity is negative 9.8. Hold on just one second. Okay, so now we have our time and we have a velocity in the x direction. Let's see if we can calculate our displacement in the x direction. But let's go ahead and see if we can't use the same displacement equation. Okay, now we've mentioned before in class that the acceleration in the x direction is 0 unless I say otherwise, right? We said that the ball was thrown at 6 meters per second off this high ledge, And unless it's got a motor on it, it's not going to get faster as it falls. So our acceleration in the x direction is equal to 0, so we can strike that out. And now our delta x is equal to 6 meters per second multiplied by 2.47 seconds, or 14.85 meters. And again, let's go ahead and write that in over here, just in case I have to erase some stuff. Okay, is that clear? Is that more clear? Okay, let me clear a little bit of space. But now let's go ahead and figure out what our velocity is in the y direction as this thing hits the ground. Okay. We've used this equation more than a few times. Delta v is equal to acceleration multiplied by change in time. And another way of writing delta v is vf minus vi equals a delta t. We know our initial velocity in the y direction is 0. So we can go ahead and knock that straight out, which leaves us with vf is equal to negative 9.8 meters per second squared multiplied by 2.47 seconds, or 24.206 meters per second. More markers just in case. Okay. Now, let's go ahead and see if we can't calculate our resultant velocity, okay? And as we're familiar with at this point, our resultant velocity, there we go, is calculated using Pythagorean theorem. R squared equals a squared plus b squared. And we already know that it doesn't matter which Vx or Vy is a or b, so let's just go ahead. 24.206 squared plus 6 squared equals 585.93 plus 36 equals 621. And then if we square root both sides, we get a resultant velocity of 24.93 meters per second. Okay. Now, I don't curve anything. You need to try hard. Anyway, so this right here, this 24.93, is possible to be a right answer. Frankly, it looks a little bit low, so I would encourage anybody out there to check my math and make sure. But 24.206 squared equals almost 600, whereas 6 squared equals only 36. So we can tell that it's going to be much closer to this one. Like it's going to be pretty close to this one. This 36 doesn't really contribute a whole lot to our overall amount. So this 24.93 is probably correct. And because it's bigger than 24.206 and bigger than 6, it could be. So we're pretty good. Now, let's go ahead and figure out our angle at the end of this. Now, more than a few people have pointed out that we could use the displacement as well as the velocities. And since, well, I mean, either one works out just as well because we have our x component. Let's go ahead and draw our resultant vectors. So our resultant velocity is this guy right here, which is made up of our x velocity, which is 6, and our y velocity, which we just figured out is, because it's negative pointing in the down direction, is 24.206. And because of that, we can use our trigonometric identity that theta is equal to the arctangent of, let's go ahead and solve for that angle right there, that this is the opposite side, so 24.206 divided by the adjacent side, 6. And make sure that your calculator is in degree mode when you're doing this. Okay, there we go. Divided by 6. And arctangent. Our angle, this angle right here, theta, is equal to 76.08 degrees. Okay, there we go. Let's see, get all that in frame. There we go. The angle is K stuff. The rest is on level. But yeah, I'm trying to make this as widely available as possible. All right, so everybody take a look or freeze frame this guy right here, and let's move on. Okay. Yes, absolutely. Mostly the main difference is the inclusion of angles. Somebody just asked if the K and L's were going to be different on the test. The K curricula mostly just has to do with the inclusion of angles as opposed to just 0 and 90 degrees. So everything else will be the same. You're right. The 24.206 was supposed to be negative, but as long as you're keeping your angles and your directions straight, it doesn't really matter. And as long as everything is clearly labeled in your pictures and your drawings, then I won't take off any points. Okay. So let's pick something else to do. Let's see. So the baseball player hits a ball at 25 degrees. The home field or the outfield wall is, let's see, 200 meters away. That's too far. Something more realistic. 100 meters away. How hard does he have to hit it to get it over the wall? Okay. Let's say the wall is 5 meters tall. So at 100 meters away, is the ball 5 meters or more? Like, how fast does it have to be for the ball to cross the outfield fence? Okay. And again, this one, if we don't have enough information, I will give more information. So let's start with the K stuff. Okay. For the K stuff, we're going to have to use some trigonometric stuff. Our Vx is equal to V multiplied by the cosine of 25. And our Vy is equal to V times the sine of 25. Okay. After that, most of the time, we're just going to be able to use them as a use them as Vx and Vy. We're not going to have to do much to it. Let's say that the outfielder can get to the home run wall in exactly 5 seconds, and the ball has to be out of the park by then, or it's going to get caught. Okay. 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 Well, let's just say if the ball is in the air for 5 seconds, how? Okay, let's go. So, all right, okay. Now I see how it's going to go. Sorry, I'm making it out. Yeah, Josie, -5 points right there. It'll be all salty. All right. Anyway, so we have a delta t. Now, from this, we can calculate what the minimum value of our Vx must be. Our Vx has to be delta x divided by our time. That's the minimum value. It can be faster, but it can't be any slower. So our Vx has to be at least 100 meters divided by 5 seconds. Okay. Now, this is a little different for K's and for L's, but again, unless you're doing this trig right here, the rest will be the same. Okay, so our Vx must be at least 20 meters per second. Okay, must be at least 20 meters per second. And with a Vx of 20 meters per second, that's equal to V times the cosine of 25. And if we divide both sides by cosine of 25, let's see what the minimum V might be. Relax. I know we haven't spent much time together as teacher and student, but is there any chance that I relax about absolutely anything? Divided by the cosine of 25. So our V, at least our first value of V, must be at least 22.67 meters per second. Now we need to test it and see if that value will get us over the wall. Vx is a velocity in meters per second, whereas delta x is a distance or a displacement measured in meters. So Vx and delta x are different, always different. Anyway, let's see if our V will get us out of the park. Now, if we have our V like this, our Vy ends up V sine of theta, or 22.067 times the sine of 25, or 9.33 meters per second. I'm trying. Okay, let me move this stuff down. All right. Okay. Again, because this appears to me backwards, it's hard for me to keep it in frame all the time. Anyway, moving on. Let's see if with 9.33 we can get all the way out of the park. Now, if we hit something at Vy is equal to 9.33, let's see how long it actually stays in the air. Now, we remember that our time is equal to delta V over acceleration. And because that's only half the time from the hit to the very top, we know that we're going to have to multiply it by 2. Remember? Good. So our delta V is just equal to this 9.33 divided by 9.81 multiplied by 2. And that gives us a total of 9.03 seconds in the air. So no, at least not at our current speed are we going to be able to get out of the park. Okay, so let's see what we might need to do in order to get out of the park. Since we're interested in our delta V, let's see if we can't just ask for 5 seconds straight off the bat. 5 seconds is going to be equal to whatever our delta V is divided by our negative 9.8 multiplied by 2. Divide both sides by 2, and we have 10 equals delta V divided by 9.8 multiplied by both sides by 9.8, and we have our delta V is equal to 98 meters per second. In order to stay in the air at least 5 seconds, we'd have to hit it 98 meters per second, which is insane. Now this delta V, remember, refers to our Vy, which is equal to V sine of theta. If we divide both sides by the sine of 25 degrees, (98) divided by the sine of 25 degrees, we'd end up with an initial velocity off the bat of 231.89 meters per second. That's like as fast as an airplane. So no, it's very much not possible, not at all. When I make up these problems on the fly, they get a little crazy sometimes. So we'll all the math is valid, but this isn't a particularly good problem on my part. So I'm going to erase this and blow my nose briefly, and then you guys are going to ask me some questions. So start thinking right now. Just start typing them into the comments. Thank you. You know what, Brian? No, it's not a question like that. Not exactly. Won't be on the test, but let's go ahead and do one that will be. Let's ask it a little more concretely. If we were to, let's do this one a little more K-friendly. If we were to throw a ball off of a cliff at delta Y, how high would it have to be in order to hit a target 150 meters away if it starts with an initial velocity of 8 meters per second? Okay, so we're going to need to calculate how fast it can travel there and get at least that much time. Okay, so first thing first, we're going to need to calculate our velocity in the x direction, and then calculate our delta y. But you know what? Let's go ahead and calculate our delta time, our Vy, resultant velocity, and our angle at the very end. Let's calculate all that stuff. No angle questions on the L test, but I'm throwing in the angle because all you have to do is disregard the angle and everything else is true for L. So I'm just trying to make every problem at least a little bit applicable to everyone who's with us right now. Now our Vx is 8 meters per second. We gave that to you already. Now, in order for it to reach the 150 meter away target, and there might be a question like this on here, we need to figure out how long we need to get from here to there, and then make our cliff at least as high. Okay, so Josiah, how do we find Vx if we don't know the angle? Now, I'm not entirely sure that you can. Your question implies that we don't have enough other information, but you know what? Let's go ahead and do the next one, have it be like that, okay? So we need at least enough time to get from here to there. And let's start where we have been starting lately, Vx, delta t plus 1/2 a delta t squared. And again, there's no acceleration in the x direction, so we can strike that out. And with 150 meters, we know our Vx is 8 meters per second, and we're trying to solve for however much time we need for that. So if we divide both sides by 8 meters per second, cancels out those 8s, and 150 divided by 8 is 18.75 seconds. So we need at least 18.75 seconds in the air. So equals 18.75 seconds. So we need at least 18.75 seconds in the air. And that's actually going to be quite high. But now that we can solve for our delta, well, easiest thing would be to solve for Vy. Let's go ahead and solve for that. Delta V is equal to A delta T, or another way to write that, Vf minus Vi equals A delta T. We know what our delta T is, and we know our initial velocity is 0, so we can strike that out. Vf is equal to negative 9.8 multiplied by 18.75 seconds. Okay? And that gives us negative 183.75 meters per second. That's quite fast. There we go. When the question asks for instance, how high, I can't remember what I'm looking for. In this case, it's delta y. When it says how high, it's going to be delta y. You just have to think which axis is that distance pointed in. Height is normally going to be in the y-axis, so that's what we're talking about. Distance, like range, is normally along the ground or in the x-axis, okay? So, you know what? We could go ahead and find our resultant velocity right now when we do that. R squared is equal to a squared plus b squared. Let's go ahead and finish this up here. R squared equals 183.75 squared plus 8 squared. We can already tell it's going to be only a little bit more than this. But 183 squared plus 64, and then square root the result, we end up with a R of 183.9 meters per second. Okay, so boom, there we go, 183.9 meters per second. Okay, now everybody got a hold of this, so I'm gonna be able to erase some of this so that I can get my room back. Okay, and let's go ahead and, well, let's calculate delta y and then do the angle at the very, very end. Okay, so our delta y, our displacement equation in the y-axis, is as we are familiar with right now, Vy delta t plus 1/2 a delta t squared. And again, our some will be multiple choice, but if you can't do them all, you're going to be in trouble anyway. So we know our initial velocity in the y direction is 0, so we can strike that out. And we don't know delta y yet, but 1/2 delta 1/2 a delta t squared, 18.75 squared. Let's see what our height needs to be. Yeah. All right. So our delta y needs to be 1,722.66 meters. Like I said, it was going to be very, very high. And then very last 1,722.66 meters. And then very last, same as before, tangent of Vx is the adjacent and Vy is the opposite. So Vy negative 183.75 divided by 8. Divided by 8. And then arctan of that is 87.51 degrees. It's going to be almost straight down. As is normally my deal, I really, really hate saying always, because all it takes is one exception to make it not true anymore. But height will normally be the delta y, and it's generally a safe assumption. Okay, if you make that assumption, it's rare that you'll be wrong. So if you need to think it that way to give yourself a more firm grasp on the material, feel free to. Okay. Anyway, let's do one last where we actually solve for an angle, and then that'll be the it. Okay. So again, I'm about to sign off in just a little bit, so ask me questions if you've got other things you want. So let's go back to baseball. If we're going to solve for an angle, V is equal to 25 meters per second. It's caught by an outfielder, let's say 80 meters away, exactly 3 seconds. Okay, so I do have a fair amount of like foundational type stuff. I have a video called Physics, Signs, and Symbols, and some stuff like that. So if you were to check either the miscellaneous playlist or the math playlist, there'll be some stuff like that. Okay, about what delta y means and things of that nature. All right, so we're going to solve for our theta right here. We know our time. Let's go ahead and just condense this a little bit. 3 seconds. Delta x is 80 meters. Our initial velocity is 25 meters per second. Let's solve for Vy. Let's solve for delta y. And we have to solve for our angle. Okay, so what we're going to do here, at least at first, is we need to figure out what angle it would take for an initial velocity of 25 projectile motion. Which of our playlists has more information and other videos like this? Projectile motion, that's the name of the unit. The playlists are organized by unit name. Anyway, so what we need is our Vx to equal our delta x divided by our total time, or 80 divided by 3. 80 divided by 3 is, nope, can't do it. Slight change. 40 meters per second. Sorry, that's what happens when I make these up. So the only thing that changes is this guy right here. Haven't done enough for it to matter yet. Okay, so V is 40 meters per second. Okay, everybody on board? Good. So with 80 divided by 3, we need our Vx to be at least 26 2/3 meters per second, or you could leave it as 80 over 3. And again, for my K kids, Vx is also equal to V times the cosine of theta. And since we already know our Vx is 80 over 3 equals 40 times the cosine of theta. If we divide both sides by 40, let me finish up here, we get the cosine of theta is equal to, divided by 40, is equal to 2/3, and we can take the arc cosine of both sides, and we end up with a theta of 48.2 degrees. Okay, so let's go ahead and knock that down first. Okay, 48.2 degrees. And I've got some more space. And then we have our Vy is just equal to V, the sine of what is now 0.2 degrees. And that's 40 times the sine of 48.2 degrees. Times 40, or a Vy of 29.8 meters per second. And again, 29.8 and 80.3, which is 26. Let's go ahead and check that and make sure. Sorry, I'm checking my math to make sure I didn't do something wrong. Okay, good. Yep. This squared plus this squared does in fact equal 40. So good. I checked my math and everything was good, because r squared should equal a squared plus b squared. And so that means 40 should equal 29.8 squared plus 80 over 3 squared. And it does, so we're good. All right. Now we solve for our Vy, which is 29.8 meters per second. And then very, very last, we can figure out what our delta y is. Okay. Now we've already figured out that our total time is 3 seconds. So there's a couple ways we can do this. We know that half the time, or 1.5 seconds, is our time to the top. So delta t top. So we could do it that way. Delta y is equal to 1/2 a delta t squared. Okay, so Hazel, when does acceleration become a zero? When that velocity is not changing. And normally that has to do with it being in the x direction. X direction does not normally change its velocity. So that is normally when acceleration would be zero. So delta y is equal to 1/2 9.8 multiplied by 1.5 seconds squared. 1.5 squared times 9.8 times 0.5 equals 11.025 meters. But let's go ahead and see what we can do with this here 29.8 meters per second. So our 29.8 meters per second, if we do it right, it means it should give us exactly 1.5 seconds in the air. So our delta v equals acceleration multiplied by time. And now we're just checking our stuff because we already calculated 0.025 meters. But delta v from 29.8 to 0 should be 0 minus 29.8 equals negative 9.8 multiplied by time. So divide both sides by negative 9.8. Oh, okay, I made a mistake. Oh, well, okay. I don't want to confuse anybody. I see my mistake, but all the math we did is solid. So I'm just going to cut it off there. All right, everything we did is solid, but I made a mistake. I forgot to divide by 2 somewhere. But all the other applications are fine. And none of these problems are going to appear exactly this way. So the mistake I made will not affect what you've done. So everything will be fine. Now, 10 seconds. Ask me questions before I say goodbye. 9, 8, 7, 6, 5, 4, 3. Yes, the quiz is like the test. 2, 1. Okay, the first 10 people that say acorn squash to me in the morning, then the first 10 people that say acorn squash to me in the morning get 1 extra point on the test. All right. I hope this was helpful. Take a look at this and all right. Haha, quite funny. Y'all know what I mean. All right. Have a great evening, guys, and I hope it was helpful, and I'll see you in class.